Long lesson for section 4.5. Hopefully this one will be a little shorter. I know it will be. Okay, so 4.6 is about modeling physical phenomenon with exponential functions. So the real thing I want to try to emphasize here is just this general concept. When you have a quantity that's changing by a certain fixed percentage per input, per time, or per distance or whatever, if the change is a percentage change, then you're always going to expect that the quantity, the amount that you'll have, will have an exponential function for a formula. Okay, so here's the same thing with a little bit more symbols involved. If this quantity n, and we don't know what it represents, is changing, maybe t is time, it's changing at a constant percentage, like 10% per year or 5% per month or whatever, then the amount that you're going to have will have a formula that looks like this. This won't be the only way to write the formula, but this will be a common way that we choose to write the formula. There'll be some constant out in front, and this is the natural exponential, and this is a constant r, and then the variable t for the function. Right? So this n sub 0, this is the initial amount that you start with of whatever it is, and this r, this constant that's upstairs in the exponent spot, that's the constant, t is the variable. That's called the relative growth or decay rate. If the thing is changing by losing a certain percentage, then we'd call it the decay, the decay rate for the function. All right, so we've certainly seen one example like this already, where we had money. Our n was measuring the money. I guess we called it a of t. But the amount of money is changing at a certain percentage every year or whatever time period we choose. But the money is, the amount in the account is changing by a percentage as time goes forward. And what we learned is that formula for the amount in the account has exactly this form. It's the initial amount, the n0, and then e, and the relative, the name for this r up here, the relative growth rate, is actually the percent that was specified. So when we have continuous compounding interest, this annual percentage rate is actually equal to the relative growth rate. Okay, so we're just going to look at a couple of other examples. So we're told we have a population of 500 bunnies. That's their initial count, I guess. And we're told that this population is increasing by a certain percentage each month. Right? That alone, that information alone tells us that the formula for the number of bunnies is going to have this form. It's the initial amount, e raised to the some constant called the relative growth rate, times t, right, where t is the number of months in this case. Now, we said that this is a mathematical model for the population, the size of the population. It's certainly not a mortal lock. The bunnies are not consulting this formula before they decide to go off somewhere and be bunnies. But we feel that this might have some merit in trying to predict how many bunnies there will be at a certain number of months in the future. Okay. Radioactive decay. So we start with 500 grams of carbon-14. Maybe that should be milligrams, I don't know. And this amount is decreasing by a certain percentage each year. Again, just this percentage change in the quantity tells us that the formula for how many grams, and I guess that's called a mass, will have this form. It'll be the initial amount times e to the rt. T is measured in years this time, and r is some constant called the relative. So here r will be the relative decay rate. So that's, oops, man, second time I botched that spelling. So this is referring to radioactive decay here. So again, this is a model for how many, what the mass of this carbon-14 will be. but it certainly seems like this is going to be a more accurate model than the bunnies. The carbon-14, it seems like, is going to be behaving in a much more predictable, uniform manner than a bunch of wild bunnies running around. Okay, a third application is called Newton's Law of Cooling. And what Newton's Law of Cooling says is that the difference between, say, the temperature of a cup of water and the atmosphere that the cup is placed into. So here the cup starts at 140 and we're putting it into a large freezer. So initially that difference in temperature is 120. Okay, so Newton's Law of Cooling says that difference in temperatures will decrease, once again, at a constant percentage. So that's what we're always trying to focus on here. When something is changing by a constant percentage, that's the cue, is that the formula for that quantity is going to be given by this formula. The formula given by a formula. Right? So this is our model for the difference in temperature, the difference between the cup and the freezer. That's the initial difference. E, of course, that's 2.7. R, the relative decay rate. T, time measured in, I didn't give units here. Okay, days, or hours, let's say. Okay, so this is the model for the difference in temperatures, and the model for the temperature of the water, I guess we should put water here, is going to be 20 plus the difference. Right, so why is that? Well, we say the freezer is large, so we're going to claim that the freezer isn't changing temperature at all. So the difference between the freezer and the cup is due entirely to the change of the water in the cup. Right, so the freezer temperature plus the difference is going to give us the temperature of the cup, well, the water in the cup. Okay, so in all of these problems, we're begging the question, so to speak, of how do we find this R? Well, there are three typical ways. One is, so again, the backdrop is the same here, is that we're told that some quantity is increasing or decreasing by a percentage, but now in this case, this first example, we're told how long it takes that quantity to double. So we're given the doubling time for the thing that we're measuring. So we start with 500 bunnies, and the units of time here are months, and so the formula for the number of bunnies, here is 500, the initial, e to the RT, and we're told that the population doubles in 9 months. So that means when we plug 9 into this formula, and then we plug it into the T spot, 9 months, we will get double our initial population. So this is how we're going to solve for T. Solve for R. Right, so the doubling time is what gives us our equation to solve, and then we're just supposed to be old hats at this now. Is it supposed to be old hat? I don't know if we want to be an old hat. Okay, so divide by 500, we get 2. Take natural log of both sides. Natural log of 2. And then R we divide through by 9. So natural log of 2 divided by 9. And as a decimal, boom, roughly 7.7%. So that's the continuous growth rate. Oh, I'm calling it relative growth rate. I guess I can put that in here, aka continuous growth rate is, I can write it as a percent, 7.7%. Okay, so that was one way. We're told doubling time. And then another common way, especially for this radioactive decay, is to be told a half-life. So this is just going the opposite direction. We start with 500 grams. Again, we're decreasing by a percentage. It says our formula looks like this. But now the bonus information that we get is that the half-life of this material is 5,730 years. Right? That means after this amount of time, we will have half of what we started with. So again, the formula, the form for it is given right here. We're told in this sentence right here that when we replace the T with 5730, what we'll wind up with is half of what we started with. We started with 500, we'll be down to 250. Right? So E, again, it's hard to see that constant following the R, so I'll turn that around. This divide through, this is a half here. Natural log 5730 equals R equals natural log of half. So R equals natural log half divided by 5730. All right, now try to get that as a decimal. Log of half divided by 5730. Okay, so this is negative. This is a negative relative growth rate. Why did this turn out to be negative? Well, between 0 and 1, the natural log is negative. Remember, the x-intercept is at 1. The graph of natural log is going down its vertical asymptote to the left of 1, so the values are negative. Many people prefer calling this, oops, I got the negative. The relative decay rate. So to be honest, I'm not quite sure on the sampling of web work problems which way that's going to go. For decay problems, if this R you come up with is negative, I'm not sure if they're going to want you to enter it as negative, or if they're going to want you to say, oh, this is a decay problem, and therefore I'm going to switch it to a positive. Okay. And I hope I'm not going to wind up drilling down too far here, but in our book, I believe actually for decay problems, our author actually replaces this R with a negative R. But I'm simply not going to do that. I want the model to look the same every time, and if the R comes out to be a negative at the end, that's what I'm going to use for R. Well, it looks... Oh, yeah, so here's the other. I kind of forgot what I was doing here. So the categories were doubling time, a half-life, and then this is just some other information that we get. So water is placed into the freezer. After 10 minutes, the cup is cooled to 110. Find the temperature for the water as a function of time. And this time we do have units, minutes. Okay, so we weren't explicitly told about this percentage change. So we're going to be on the hook for this. We're going to have to just remember that Newton's law of cooling is saying that the difference is decreasing at a constant percentage. All right, so again, the initial difference in temperature, 140 minus 20, that's 120. So the model for the difference in temperature is going to be 120 e to the RT. That's what Newton's law of cooling says. So the model for the actual temperature, again, this is assuming that the freezer stays constant. The model for the temperature of the water is going to be 20 plus the difference in temperatures. Okay, so working out the model is a little bit, it takes one more step to deal with this difference issue. But now we're just going to apply the additional information that we were given. So this is the sentence right here in symbols. translates to W of 10 equals 110. All right, so this is the other kind of type of information that you get, just some stray other time. Okay, but the method is still the same here. We're just simply going to take the formula as we know it has to look like and plug in, let's see, 10 for the t, 110 on the other side, and then begin to solve it. And I could probably check out at this point, but I'll go ahead and try to finish it with you. It's 10r up here. Let's see. What did I do here? I subtracted off the 20. And now I'm going to divide through by 120. Oh, that seems like it should be something I recognize. I think that's going to be 3/4. You can go to your calculator. It's a 0.75. And then natural log. And then lastly, R is natural log 0.75 divided by 10, and I'll get that as a decimal. Log 0.75 over 10. So again, this is negative. The water is cooling as time goes on. So this is, we can think of the temperature as decaying over time. All right, well, yay for us. It was a shorter lesson today. We'll see you all tomorrow.